In the last lecture, we have defined two important properties of a dynamical system. So let F be a homeomorphism of a space X and we say that F is topologically transitive if there exists a point X such that its positive trajectory is dense in X. So the positive trajectory is the set of points F to Kx for non-negative K is dense in X. And clearly this is equivalent to the statement that the closure of the positive trajectory is X. And the second property, F is topologically mixing. This property means that for any two open subsets U and V of X, there exists a non-negative N such that F to N U intersection with V is non-empty. I will discuss relations between these two properties, and to make the presentation just more transparent, I will assume that the phase space is a metric space. X with metric dist. First, I will show that for good spaces, a topologically mixing homeomorphism, a topologically mixing dynamical system is topologically transitive. I will recall a definition from topology. I will recall that a point X is isolated if it has a neighborhood such that X is the unique point in this intersection. So X has a neighborhood, X, the point X, such that there are no other points of the space X. And the space X is perfect if it does not have isolated points. And the first result, which I will prove, I will show that if the phase space X is perfect, then topological transitivity implies topological mixing. I'm sorry. Just, of course, the converse statement. One moment. No. This is a correct statement. I will need a simple lemma. If X is perfect and Y is a dense subset, then for any open set W, the intersection of Y and W contains infinitely many points. I will write in this way the number of elements of the intersection is infinity. So in a perfect space, every dense set has infinitely many distinct points in any open subset W. Let us assume the converse. So there is an open set such, and a dense subset Y, such that this intersection consists of a finite set of points. Let these points be x1, xn. Since the set W is open, there exist open sets d1, dn, such that each of them contains one of these points. And these subsets are disjoint. So we take this open set W points. We have a finite number of points, and in the metric space they have non-intersecting neighborhoods, non-intersecting. At the same time, since the set Y is dense, one moment. At the same time, since my space is perfect, any set di contains a point yi, which is different from xy. These points are not isolated because X does not have isolated points. And if I take xi di, it contains some other point y I from X. But since di is open, there is an open set gi open. Gi contains yi, and xi is not the point of gi. So a picture like this. But now, since my set y is dense, this open set contains a point belonging to y. This point cannot be xy because xy is not in gi, and it cannot belong to any of the sets d1, dn, because gy is a subset of di. So z does not belong to d1, dn. And this is a contradiction with our assumption. This is a contradiction with our assumption. we found one more point of y belonging to W. And now I show how our theorem follows from this lemma. So proof of theorem 1. Take any open sets U and V in X, and take this point X such that the closure of X, its trajectory is X capital. So Fk to X is dense in X. Then there exists, since it is dense and the point and the set U is open, there exists a K0 such that F to K0x is in U. At the same time, we have shown that this dense set contains infinitely many points in any open set, in particular in V. And it follows that there exists a K1 more, which is more than K0, such that F K1x is in V. So what do we see? These are U, V, F K0 F X, F K1 X with K1 larger than K0. Of course, this means that F to K1 minus K0 of U intersection with V is not empty. And this number is positive. So in perfect spaces, topological transitivity implies topological mixing. And now I will describe the situation in which topological mixing implies topological transitivity. If X is a compact metric space, then topological mixing implies topological transitivity. This theorem has been proved by Birgov. And the construction which is used in its proof is very important, the Birkhoff construction. Since X is a compact metric space, it contains a dense countable subset. There exists a set of points AN, let indices be not less than 1, such that this set is dense in X. More than that, I can assume that, how to say, any tail of this sequence is also dense in X. So in addition, we assume that for any n capital, the set is also dense. This is, if you look at the proof of the existence of a countable dense subset in a compact metric space, you can see that you always can construct a dense set with this property. Consider sets Dn which are open balls of radius In centered at these points. This is why I take n starting from unit here. So these are balls of radius 1 over n centered. Now it's an easy exercise to show that if I have any sequence Bn such that Bn belong to Dn, then this set will also be dense. In X. It's an easy exercise for you. And I want, now what do I want to do? I know that my dynamical system is topologically mixing. And I want to construct such a set which is a positive trajectory of some point. Well, let me start the construction. Take two sets of that kind, D1 and D2. They are open subsets of X. And the topological mixing property implies that there exists a number n2, non-negative, such that f to n2 d1 intersects d2. So I have the point x1, this ball d1, point x2, this smaller ball d2, and positive one of images of d1 with non-negative degree intersects this means that there is a point, I will call it C2, in D1 such that f to n1 C1 is a point of D2. But this intersection is open. The image of D1 under this homeomorphism is open, D2 is also open, so this set is open. And hence there exists f and 2 d1 is open. Hence there exists an open set, I will call it C2 capital, such that it contains this point and its image under this degree, to be exact, not its image, but the image of its closure, also belongs to D2. And of course I may assume that this closure is a subset of D1. So we have here an open set such that its closure belongs to D1 and its image belongs to D2. Clearly, for any x in C2, x is in D1, f and 2x is in D2. So the positive trajectory intersects both sets D1 and D2. And now we continue this procedure. I take this set C2 capital. It's an open set. And I take the next ball. D3. And I repeat this construction. We have topological mixing, so there exists some N3 non-negative such that F to N3 of C2 intersects D3. And I construct an open set such that its closure is in C2, and at the same time F to N3 of this closure is a subset of D3. Then, of course, for any x in this closure, x belongs to D1, F to N2, x belongs to D2, because of course I can take it in C2, and for x from C2 this is true, and F to N3 of x, and so on. So I get a sequence of a nested sequence of these compact sets, D1, C2, C3. It has a non-empty intersection. And for any point in this intersection, its positive trajectory intersect any di. So we have constructed a dense positive semi-trajectory, and we have proved that F is topologically transitive. Now I want to understand what happens, what do we know about our two main examples. Do they have these properties? Our first example was the Bernoulli shift on the space of binary sequences. So the phase space X was the space of infinite sequences. And sigma was the Bernoulli shift. Of course, this space is perfect. It does not have isolated points. In any neighborhood of any point, there is a different point. And we have shown that sigma is topologically transitive. It was shown. So by theorem 1, it's also topologically mixing. In fact, the same is true for the hyperbolic automorphism of the two-dimensional torus. It has both properties, but here the proof is not that simple. And I will only give an idea of the proof. But I hope that it's easy to reconstruct the whole proof from what happens. So what did we do? We started with a linear mapping of the plane with this matrix, and we, after the identification, when we considered the two-dimensional torus as the plane after identification of points whose coordinates differ by integer numbers. And we got this mapping of the torus, which we model on the unit square of the plane. Of course, this phase space is a compact metric space, and I want to apply theorem 2. I want to apply the Birkhoff theorem to show that F is topologically mixing. And then by theorem 2, it is topologically transitive. Let me first understand what happens in the plane. It is easy to calculate the eigenvalues of this matrix. The eigenvalues are like that. One of them is positive and between 0 and 1. And the second one is more than 1. If I look at the eigenvectors, I denote them Vs and Vu. Vs is the eigenvector for lambda. We will see later why this subscripts appear. In fact, they correspond to stable and unstable. There, the first letters. And you can see that components of Vs have different signs, because if I write the matrix, if this is the matrix A, then A minus lambda, it will be and you can see that coefficients for the eigenvector satisfy a linear equation with coefficients of the same sign. So in fact, and if I take here 1 over lambda, they will have different signs. So Vu will have components of the same signs, of the same sign, and since lambda is irrational, the angles will also be irrational. So the relation between components of both eigenvectors will be irrational. Now I want to show that my dynamical system is topologically mixing. Take an arbitrary open set U on the torus. Of course, I can treat it as an open set in this unit square. We know that periodic points of my dynamical system are precisely points with rational coordinates. They are dense. So I can find a periodic point P. U is an open set. There exists P in U, and let M be the period. Fm of P equal P. Consider a straight line containing the point P and parallel this line L parallel to this eigenvector corresponding to 1 over lambda. And consider a small segment. So U, P, L, and a small segment, let it be L prime, containing P. What happens with this segment under the action of my F? If I look at the plane, let it be the point P tilde corresponding to P and line L tilde corresponding to L. L tilde is parallel to this vector. So if I take this L prime tilde, it will be, so my point P is mapped, point P is mapped somewhere here, say let it be R, but the line is parallel to the eigenvector, so it goes to a parallel line, and the length of this segment, if this is, say, L2 prime. L2 prime is the image of L prime under this linear mapping. Then its length will be 1 over lambda, the length and this will repeat. So under action of any degree of F, the length of this segment will be multiplied by the corresponding degree of 1 over lambda. And when after m steps, after m applications of F, I return to this point of the torus, I will get something corresponding to a segment of this line, and its length will be the total length lambda to minus m length of L prime. And of course, on the torus I will get something like that. When the line goes here, goes here, then here, and so on. So on the torus I will get a system of parallel segments with total length And the slopes are irrational. In the plane, the slope of this line is irrational. It is irrational here as well. And here I will refer to some easy statement, which I leave to you. So for any positive epsilon, there exists a positive L such that if I have a segment of a line whose length is more than L total, then the corresponding set on the torus will be epsilon dense. The set of these segments will be but my lengths after any I can apply f to m, f to m, and so on. So on the torus I will return to the same point. And I will get a system of these segments which is epsilon dense, where epsilon is as small as I want. So if I return to the notion of topological mixing, I take this open set U. I can take as small as I want segment L prime, so that L prime is a subset of U. I take any open set V, and images of this small segment will be epsilon dense. The union of images will be epsilon dense in the torus with any epsilon. So of course one of them will intersect V, and this means that some point of U will come to V after a large number of steps. And now we can apply the Birkhoff theorem to show that the hyperbolic automorphism of the torus is topologically transitive. Okay, so we have looked at some simple topological properties of dynamical systems. And now I want to consider two classical examples in the theory of dynamical systems. In fact, these examples were the base, the foundation of what happened later. One of them are mappings of the circle, homeomorphisms of the circle. And the other system is flow in the two-dimensional plane. So I will unite them I will speak about low dimensional dynamics. And I start with discrete systems in dimension 1. And the topic will be the rotation number. This is a very important characteristic introduced by Poincaré. So, what will we study? Consider the circle S. It is convenient for me to introduce a coordinate identifying 0 and 1, and also I introduce direction on the circle. And I want to study homeomorphisms of the circle and their properties related to the rotation number. The simplest situation is the situation of a homeomorphism of that type. Fx is x. Let me keep my notation plus mu. This is just the rotation of the circle at some angle. Of course, I may assume that mu is not We have seen this example when we considered embedding of a homeomorphism into a flow. And we have seen that if mu is a rational number, then every point is periodic. If mu equals 0, then of course every point is a fixed point, and if mu and I take f to k n, it will be x plus k n m over n. So, of course, k to m is an integer. So, n is a period. Oh, all these numbers are periods. We have a completely different picture if mu is irrational. As I said, in this case, every trajectory of my homeomorphism is dense. on the circle. First, we note that f k x is x plus k mu and it is not x for any case, so the trajectory consists of a countable number of points, and this set is dense. I will give a simple classical proof of this. So take an arbitrary epsilon, positive epsilon, and cover S with segments of length less than epsilon for any Of course, I can cover S by a finite number of such segments. And since I have a countable number of different points, there exist two different numbers m and n such that fmx and fnx belong to the same segment of length less than epsilon. So I have this segment with length less than epsilon, and I have 2 points. But of course, geometrically, my mapping is a rotation. So if I assume, for example, that n is larger than m, and denote by g f to n minus m, then g takes this point to this one. And p, g of p, and this is less than epsilon. And since my mapping is a rotation, it will move points, the arcs g square. Every arc will have length less than epsilon. So for g, I have found a trajectory which is epsilon dense in the circle. But since I can take any positive epsilon, I get, of course, I get a dense set. Now we turn to the general case. We pass away from this linear example, but we will return to it. It will be useful for us. And now I define the main class of systems which we work with homeomorphism preserving orientation. So for any 2 points, I consider my circle S. I take 2 points P and I say that homeomorphism F preserves orientation. So in this case, I say that Q goes after P. We have this direction on the circle, and I will denote this arc, closed arc, by PQ, this arc. So the definition of preserving orientation is like that. F of PQ is F P FQ. So if I take the images, then this arc is precisely the image of that arc. Of course, this rotation is an example of a homeomorphism preserving orientation. I didn't say, but of course it's a homeomorphism. The inverse is x minus mu modulus 1. And now I define, following Poincaré, I define the rotation number. Take any point P, consider its image, and let the length, denote the length of this arc by alpha 1 of P. So we take P, we take its image, we take the arc when we go from P to F at P, and the length, then I take F square, the length is alpha 2 of P, and so on. Alpha n of P is the length of this arc. And let me denote by phi n of P the sum So what happens? We look at a point And we look how, in a sense, it rotates around the circle. The length of the first arc, the length of the second arc, and so on. And now we introduce the main characteristic which we study, the rotation number, tau of f. It's the limit as n goes to infinity, phi np over n. Of course, at the first glance, this may look strange. Here start from some point P, but here I use no P in notation, and this is the first important fact, that this number does not depend on the point P. And just this number, it's a characteristic of my homomorphism, is the rotation number. So the first important theorem states that the limit exists and does not depend on the initial point. We state that it exists and is independent of P. I will start with the second statement, independence. Let me look at 2 points, P and Q. Since my homeomorphism preserves orientation, the order of the images is the same as the order of the points. So if I denote this initial arc from P to Q by A, what I see, this is alpha 1 of P, and this is alpha 1 of Q. And it is easily seen that alpha 1 of q, the length of this arc, is the length of this arc plus this is f of a. So this length is the length of this joint arc, and the length of this joint arc is alpha 1 of p minus we take this arc of length alpha 1 of p, subtract the length of it, and add. And it is easily seen that we have formulas of that type. And so on. So when we add them, we can see that phi n up here q, of course. The sum of this is the sum of this q phi p plus the length minus the length of a. And now my first statement, independence of p, follows immediately, because for two different points p and q, the denominators will differ by a number not more than 1. Well, now the first statement its proof. In the proof we have to consider two different cases. Case 1 is the case where f has a periodic point. Let P be a periodic point of period M, minimal period M. What does that mean in terms of this number phi n of P? I have my point P. I go along the circle, and I come to the same point after application f to m. So the sum of these lengths is an integer number. The length of our circle is 1. So there exists a number L such that what we can say about phi 2n p. We performed m steps. I'm sorry. Fine. After m steps, we came to the same point. Now we repeat this procedure. We again make m steps, coming to the same points, and we again get the same number. So it will be 2L. L for the first m steps and L for the steps from m plus 1 to 2m. And so on. Phi n mp will be 2L. Will be Ln. If I divide this, if I multiply this by m and divide by L and m, I get phi n m p divided by n m. Is L over m. And now, since this limit, so the limit exists and it equals L over m, and this is the rotation number. This is also important for us. So if I take a periodic point of minimal period m and before returning I make L complete turns, then the rotation number is this value. Well, and since the case where f doesn't have periodic points takes more time, we'll stop here for today.